The Monarch 10EE swings 12.5 inches over the bed and takes 20 inches between centers. It weighs around 3,000 pounds. The factory specified its spindle to run within 40 millionths of an inch, and the machine has been in continuous production since 1939. It is also the lathe that gets named more than any other when somebody asks what the best manual lathe ever built was. So is it really? This is Trade Archive, where we take apart the machines that built everything else. Hit like and subscribe before we start, because this one runs long. The 10EE was not designed in isolation. Monarch developed it with Western Electric of Chicago, and Western Electric wrote the initial specification for the machine. The first units went to Precision Scientific in Chicago and to Woodward Governor in Rockford, Illinois. The brief was accuracy and surface finish, not capacity, and the machine reflects that in every dimension. The 1939 machine swung 12 inches, took 20 inches between centers, carried a D13 camlock nose, and ran 25 to 2,500 revolutions per minute. The spindle bore is 1 and 13/32 inches. The spindle runs in super precision angular contact bearings with a 60 millimeter inside diameter, hand-matched in sets, with a special flanged bearing at the front. The tailstock is a No. 2 Morse taper, sleeved down from the original No. 12 Jarno, with 3.5 inches of quill travel. What separates it from everything else on this list is the drive. The 10EE has never used a conventional geared head. The 1939 machine used a Sundstrand hydrostatic drive, infinitely variable across its whole range. In 1941, that was replaced by a Reliance motor generator set in a Ward-Leonard arrangement. An AC motor spins a DC generator. The generator's field winding is what the operator's speed control actually adjusts, and the generator feeds a 3-horsepower DC motor driving the spindle. Because a DC motor's torque follows current rather than speed, the machine holds full rated torque anywhere in the range, including at the bottom of it. That is the property no belt or gearbox on this list can reproduce. In 1949 came the vacuum tube drive, known to owners as works in a drawer, which used thyrotron tubes to control the field and ran on single-phase power. The 1960 modular drive brought a 5-horsepower DC motor, and around 3,000 were built. A solid-state DC regenerative drive followed in 1984, an AC inverter drive on a 7.5-horsepower enclosed motor in 1995, and factory rebuilds today use a 5 or 10-horsepower 3-phase motor on a variable frequency drive. On a geared lathe, you pick the nearest available speed and live with it. On a 10EE, you dial the exact surface speed the material and the tool want, mid-cut if necessary. The rest of the machine protects that spindle from anything that would disturb it. The drive sits in a one-piece cast base. Isolating it from the bed, the spindle is belt-driven so motor vibration never reaches the work, and during feeds, a flat belt drives the gearbox to keep gear impulses out of the finish. The bedways are flame-hardened, which matters more than it sounds. A soft bed wears fastest in the first few inches ahead of the chuck, where most cuts get taken, and it wears into a bell mouth. The carriage then drops as it travels away from the headstock, and the machine cuts a taper nobody asked for. No spindle specification survives that, which makes the hardening a precision feature rather than a durability one. Owners divide the machines into round dial and square dial by the shape of the speed control housing, and the distinction is not cosmetic. Square dial machines added a spindle safety interlock and a high lock preventing back gear engagement above 250 revolutions per minute. Round dial machines have neither. A rarer option called ELSR gave the machine electronic lead screw reverse, which lets the operator thread up to a shoulder and reverse out without disengaging the half nuts. The buyer list followed the specification. Precision instrument makers took the early machines, and government work took most of what came after. Surviving 10 EE machines turn up carrying War Department and Detroit Ordnance District plates, and the Hanford site in Washington state ran them. Those machines got maintained on a schedule and rebuilt rather than replaced, which is why a 1940s example can still be bought in working order. The 10 EE is also the machine on this list with the most documented weaknesses, and they are worth stating plainly. The drive is the first. The motor generator and vacuum tube systems are obsolete and expensive to repair, and individual thyratron tubes for a works-in-a-drawer machine run into the hundreds of dollars each when they can be found. Converting to a variable frequency drive solves the parts problem, but loses features, and a bad conversion destroys the low-speed torque that was the point of the machine. The second is capacity. 20 inches between centers is short, and a 30-inch bed was offered that almost nobody bought. The headstock is long, the useful working length is not, and anyone turning something slender runs out of room fast. Third is the tailstock, consistently described as light relative to the rest of the machine, and the one component that does not match the mass around it. Fourth is parts beyond the drive. Gearbox gears and lead screws are proprietary and interchangeable with nothing, and priced accordingly. And fifth is the weight. 3,000 pounds in a machine of this capacity makes it expensive to move, and rigging is a real part of ownership. The 10 EE is the best all-around precision tool room lathe on this list. It holds a spindle specification in millionths, and it still has enough torque and enough back gear to take a serious roughing cut. Very few machines do both. The machine that took the most work away from it did only one of those two things, and did it better. Hardinge described the HLVH in its own sales literature as filling the gap between the plain precision bench lathe and the heavy-duty engine lathe. The HLV came first, the HLVH added higher speeds, and the EM variants added a dual gearbox for inch and metric. The machine stayed in production over 60 years, and a later electronic version replaced the mechanical threading arrangement with a servo threading computer on a 5-horsepower motor. The dimensions are close to the Monarch. The character is not. 11 inches over the bed, 18 inches between centers, and a 1.25-inch spindle bore. Spindle speed is variable from 125 to 3,000 revolutions per minute through a mechanical variator in the headstock, with a 2-speed main motor running 530 and 1,710 revolutions per minute. The tailstock is a number 2 Morse with 3.75 inches of quill travel. Threading covers 11 to 108 threads per inch, reached through somewhere between 27 and 36 gearbox settings depending on the machine. The defining feature is the spindle nose. It is a Harding taper that accepts 5 C-collets directly, with no adapter, no closer plate, and no intermediate component to introduce error. On most lathes, a collet sits in an adapter which sits in the spindle, and every one of those joints contributes runout. Removing them is worth more than any single bearing upgrade. Hardinge's published figure for maximum spindle runout is 25 millionths of an inch. Machines rebuilt to original specification by Babin Machine are test cut to 50 millionths of taper over 3 inches, and the Plumier Foundation's rebuilt example is documented at 25 millionths total runout. That nose also settles the tooling question. 5C is still manufactured in every configuration from round and hex to emergency and step collets, so a Hardinge can be tooled from a current catalog. Very little else here can. The bed is a dovetail section chosen for rigidity. Carriage and one-piece tailstock are both hand-scraped to full bearing contact, and the spindle is preloaded to remove end play and radial play. The machine sits on a 3-point pedestal, so it defines its own plane and cannot be twisted by an uneven floor, which is why leveling is not required to hold alignment. Feeds are driven by a DC motor mounted on the apron itself, rather than taken off the spindle through a train, which is what makes the HLVH the easiest machine here to thread on. Threading ergonomics are why a lot of toolmakers preferred it over everything else. The limitations follow from the same design. There is no back gear, so no torque multiplication at low speed, and the motor is small compared to the Monarch. Heavy cuts and large diameters are outside its brief. Metric threading on an inch machine is slow and awkward unless the dual gearbox is fitted. The flat surfaces on top of the dovetail bed hold grit if the machine is not kept clean, and a Harding used as a general-purpose lathe wears out of specification faster than its reputation suggests. The design was also copied widely enough that clones from Feeler, Royal, and others still turn up on the used market. The 10EE and the HLVH have been compared against each other for decades, and it is worth being precise about where that comparison comes from. The sustained head-to-head argument is mostly a product of machinist forums from the early 2000s onward. It does have a genuine period foundation. A 1963 purchase requisition raised to replace two existing 10EEs cross-shopped 3 machines for the same tool room role: the Harding, the Monarch, and the Rivet. Those 3 were the shortlist, in period, for the same job. The Rivet is the least known of the 3, and arguably the most machine of the 3. A wartime 1020 came first, with a rare variant called the 1020R. The 1020S and 1030S that followed were built between 1949 and 1961, differing only in bed length, at 20 and 30 inches between centers. Later F models raised the swing to 13 inches and replaced the mechanical tachometer with an electrical one. The 1020S weighs 3,800 pounds and the 1030S 4,200 against roughly 3,000 for a 10EE of the same capacity on a 5-horsepower drive. Open belt speeds run 280 to 2,500 revolutions per minute, or 400 to 3,600 depending on configuration, with 2 separate sets of back gearing underneath, giving 22 to 244 to 400. Threading covers 2 to 240 threads per inch. The spindle came with an L0 taper as standard, or a 4-inch D1 camlock as an option, and takes 6 R collets directly to a capacity of 1 1/8 inches. All gearing is heat-treated and ground. Anyone who has stood in front of both notices the headstock. The speed control knob and tachometer sit in nearly the same arrangement as the Monarch, close enough that the two look related, though the record does not settle which came first. The detail that matters is inside that headstock. The rivet spindle carries an additional middle bearing, making it longer and better supported than the equivalent Monarch spindle. A spindle deflects most where it overhangs its front bearing, and that deflection is what a heavy cut at the chuck feels like at the tool. A third bearing shortens the unsupported span and stiffens the assembly against exactly that load. Combine it with a footprint of 29 by 73 inches and 2 ranges of back gear, and the rivet is the most rigid machine in this size class. Its variable speed drive is entirely mechanical, which removes the single biggest ownership problem of the Monarch 10EE. There is no generator, no tube, no drive board, and nothing to convert. What it gives up is support. Parts and tooling for a rivet are thin. There is no factory to call, and the 6 R collet series it uses so elegantly went out of production with the machine. A rivet bought without its collets is a rivet that will be hunting collets for years. The rivet is best at toolroom precision, where the cuts are heavy. It is a Monarch 10EE with more mass and more gear range and fewer electronics. 3 machines in, and everyone has chased precision by adding mass. The Schablin 102 goes the other way and answers a different question entirely, which is how small and how accurate a part can get. The design traces back to the American W.W. Pattern watchmaker's lathe, and within Schablin's range, it is a grown-up version of the smaller Schablin 70. It has been in production more than 80 years. The toolmaker version, the TO102, is the one instrument makers and horologists want because it accepts W20 or W25 drawback collets and uses a screw-operated carriage. There is a second operation version, the TL102, and a turret version, the TR102, and the machines came bench-mounted or on a cast base as the 10280. Center height is 102 millimeters, which is where the model number comes from. Swing over the bed is 200 millimeters, and over the cross slide 120. Between centers runs 300 to 470, depending on bed. Spindle bore is 20 millimeters on the W20 machines. Speeds run 40 to 3,000 revolutions per minute on older machines, and later variable speed and integrated motor versions reach 5,000 to 6,000. Bench machines weigh around 130 kilograms. On a cast stand, they run 450 to 560. Motors range from 0.37 kilowatts on early machines up to about 3 on the latest. The headstock casting is substantial out of proportion to the machine. The spindle is hardened and ground, and the drive uses a stepped cone pulley where the largest pulley also serves as an index plate, so the same component that sets spindle speed also divides the work for milling and drilling operations without a separate dividing head. The W-series collets are draw back rather than push out. Tightening pulls the collet into its seat and pulls the work toward the spindle, so the part does not shift axially as it clamps, and the seating force loads the taper rather than spreading it. That is why the machine holds position on a part measured in single millimeters. The collets are exceptionally accurate and correspondingly expensive. Lubrication is oil throughout, not grease, and the machine is unforgiving about it. A Schaublin spindle that has been packed with grease by a previous owner is a rebuild, not an oil change. Machines built before 1990, particularly the N series of 1979 to 1989, were hand-fitted by Schaublin staff, and those are the examples instrument makers pursue. Simonet, also Swiss, built near-identical machines with interchangeable parts, worth knowing when tooling is scarce. The Schaublin 102 is the best machine here for horological, instrument, and micro-precision work. It is not a general-purpose lathe and was never meant to be. Britain built its own answer at full toolroom size. The Holbrook Model C occupied the same tier there that Monarch and Rivet occupied in America, and got there by a different route. The C range was built from around 1940 until the late 1960s in 5 sizes: the C10, C12, C13, C15, and C16, with the C10 the most common. A 1946 advertisement offered them at 10, 13, and 16-inch swings, rated at 2,000, 1,500, and 1,000 revolutions per minute. High figures for a British toolroom lathe of that period. Alongside them, Holbrook built the Model B No. 8 bench lathe, a variable speed machine called the C8 Electronic, and the smaller Miner. The bed is an American-style double V section of heavy proportions. The spindle runs in plain hydrodynamic bearings fed by pumped oil rather than in rolling element bearings, and that single choice is what gives the machine its finish. A rolling bearing carries load on discrete contact points, and every ball that passes under load generates an impulse at a frequency set by the geometry. Those impulses reach the tool. A hydrodynamic bearing has no contact points. The rotating spindle drags oil into a converging wedge and rides on the pressure that develops, separated from the housing by a film that also damps vibration. The film stiffens the faster the spindle turns, which is why owners run these spindles above their nominal ratings, and why Holbrooks went to the Atomic Energy Research Establishment in numbers and were used for optical chasing. The trade-off is that the film only exists while the spindle turns and the oil flows. Start under load before it has warmed and circulated, and the shaft runs on metal. A neglected Holbrook spindle is a scraping and line-boring job rather than a bearing swap, and parts are scarce. The Holbrook Model C is the best machine here for high-speed precision turning, where the finish is the deliverable. Finish is one problem. Taking a heavy cut and still holding a tolerance is another, and the Dean, Smith & Grace 1307 moves the argument up a weight class to meet it. The number is the specification. 13 inches nominal swing over the bed, 7 inches over the cross slide. Earlier machines had been named by swing and bed length, as in 13 by 42, and the switch to paired digits came with this generation. The new 1307 ran from around the late 1960s into the 1980s. Actual swing is 14 inches, or 355 millimeters, with 7 inches over the cross slide and 22 inches in the gap. Between centers is commonly 40 inches, with 30 and 50-inch beds offered. The spindle bore is a little over 2 inches, running a D16 camlock nose. Dean, Smith, and Grace is credited as one of the originators of the camlock spindle nose. The headstock is all geared 12 forward speeds, typically running 29 to 1,600 revolutions per minute on 7.5 horsepower, and up to 10 on some machines. Weight is around 5,500 pounds, rising to 3 tons on later units, and the tailstock is a number 3 Morse. Later 1307s used gamut double-taper super precision bearings in the headstock. A taper roller carries both radial and thrust load in one bearing, and mounting a pair in opposition lets the spindle be preloaded against itself, so cutting force in either direction is taken without the spindle moving. That is what allows a 2.5-ton geared machine to still hold a tolerance while it is taking a heavy cut. Between the drive and the spindle sits a matrix-wet duplex clutch, running in oil, with separate elements for forward and reverse. On a machine turning a large chuck, starting and stopping through the motor shock loads everything downstream. A wet clutch slips deliberately for the moment it takes to bring the mass up to speed, and the oil carries away the heat that slipping generates. Lubrication is a full oil bath with a separate pump dedicated to the threading gearbox. Inch and metric threading are both available and switch over with 2 levers rather than a change gear swap, with diametral pitch and module available through change gears, cut to the British standard of 1963. Rolls-Royce specified these machines and recommended them to suppliers, and documented 1307 users include Thales Defence Work in Australia and the Hanford site. The complaints are consistent. The machine is top-heavy when moved, the chucks are heavy enough to be a 2-person job, the tailstock is stiff to slide, and accessories are scarce. The direction lever is also inverted compared to most lathes, up for forward and down for reverse, which catches out anyone coming from another machine. The 1307 is the best heavy toolroom lathe here. It has the geared head and the mass to take a real cut, and the bearing quality to still hold a tolerance when it does. Every machine so far has asked the operator to work around it. The Cazeneuve HBX 360 was designed the other way round, and it is the most modern machine here in the way it handles. The HB series was designed by Henri Brouet in 1949 as his engineering diploma project, and the initials are his. Around 40,000 HB machines were produced across 50 years, including roughly 6,000 built in a Cazeneuve factory in northern Tokyo between 1959 and 1973 for Southeast Asian and American customers, and further machines built under license in Spain by Amutio. The 360 HBX that followed carried an X for experimental and incorporated Brouet's patents from 1950 through 1964. Its direct descendant is still built today as the Optimax 360. Center height is 180 millimeters, swing over the bed 360, over the cross slide 190, and between centers 750 to 800. Spindle bore is 37 millimeters, and speed is infinitely variable from 50 to 3,000 revolutions per minute. The motor is around 5.2 kilowatts, the tailstock a number 5 Morse, and the machine weighs about 1,300 kilograms in a footprint of 2 meters by 1. Speed is changed by a belt variator driven by a hydraulic servo, controlled by a small lever on the apron. The variator splits each pulley into 2 cones facing each other. Squeeze the faces and the belt rides at a larger diameter. Open them, and it drops to a smaller one. Because the 2 pulleys move in opposition, the belt stays tight, and the ratio changes continuously. The operator changes speed without stopping the motor and without leaving the work. The same hydraulic pump lubricates both the spindle and the feed gearboxes, and the machine will not start if oil pressure is insufficient. The threading arrangement includes a release that lets the operator turn or thread up to a stop and return automatically to the correct pitch in metric or Whitworth. On most lathes, threading to a shoulder means disengaging the half nuts at exactly the right moment and picking the thread up again next pass, which scraps more parts than any other manual operation. The Cazenove takes the timing out of it. Both lead screws run in sealed oil baths. The operator is shielded from chuck, coolant, and swarf, and bedways were supplied, hardened or unhardened to order. The HBX 360 is the best machine here to actually operate. Everything that is a deliberate procedure on the older machines is a lever movement on this one, and the design was good enough that it is still being manufactured. Everything to this point has been a precision machine of modest capacity. The last one is not a toolroom lathe at all, and including it is the point. The American pacemaker was built by the American Tool Works Company of Cincinnati in the streamlined styling of the 1940s, in sizes from 14 inches through 16, 20, and considerably larger, in configurations sold as Style C, Style D, BCDL, and 20D. Machines ran across heavy industry from the 1940s into the 1970s, including shipboard machine shops such as the one aboard the USS Samuel Gompers. Capacity is the whole argument. Swing over the ways runs from 20 inches to 44 and beyond, and between centers from 36 inches out to 22 feet. Spindle bores run from 2 to 2 and 7/8 inches, with a number 7 Morse nose and a number 6 tailstock on the heavy machines. A medium machine might offer 18 speeds from 20 to 1,200 revolutions per minute, a smaller one reach 4,000, and a heavy one run as low as 4. Motors run from 8 horsepower up to 40. The construction details are what earn it a place. The bedways are hardened and detachable, meaning they are bolted strips rather than machined into the casting. A worn bed on a conventional lathe goes to a way grinder, which costs more than most lathes are worth and removes metal that cannot be put back. On a pacemaker, the ways are replaceable, which is the difference between a machine with a service life and one with a service interval. The spindle runs entirely on roller bearings. The carriage has power rapid traverse, because on a bed 20 feet long, hand cranking between operations is a measurable part of the working day. The signature component is the clutch, which is how the machine starts and stops several hundred pounds of rotating work without shock loading the drivetrain. It is also the known weak point. A clutch out of adjustment slips under heavy cut, and because a slipping clutch generates heat and heat glazes the friction surfaces, a neglected one gets worse rather than staying the same. Adjustment is the most important maintenance item on the machine. Early pacemakers were built without hardened ways, and later ones with them, which makes way condition the first thing to check on any surviving example. The pacemaker is the best heavy engine lathe here. Nothing else on this list can take the cut, and it was never asked to hold millionths. 8 is a limit rather than a verdict. 4 machines came close. The Weiler Matador is the German answer to the DSG 1307, built to exceed the toolmaker accuracy grade of DYN 8605 and the market leader across German-speaking Europe for decades, and it lost its slot only by overlapping ground the Cazenove and the Dean, Smith, and Grace already cover. The Schaublin 135 and 150 are the larger Swiss toolroom machines, built to the same standard as the 102 with the capacity for general work. The Colchester Mascot and Triumph and the Harrison M300 and M400 are what most British shops actually had, well built and everywhere, and a clear tier below the precision leaders on spindle specification. And the Myford Super 7 is a light machine designed for model engineering, which makes putting it against a rivet a category error rather than a comparison. Line the 8 up and the clearest division between them is not country or decade. It is how each solved the speed problem. The Dean, Smith & Grace, and the pacemaker use a geared head. Gears give torque and never slip, and the cost is that every gear tooth impulse travels into the cut and the operator only gets the speeds the gearbox was cut for. The Hardinge and the Rivet use a mechanical variator, buying infinite adjustment inside a range while staying repairable with hand tools. The Schaublin keeps a cone pulley and a belt, the oldest arrangement here, and takes its refinement from bearing quality instead. The Cazenove puts a hydraulic servo on the variator so the operator never leaves the apron, and the Monarch went electrical in 1941 and stayed there through 6 generations, which bought it what no mechanical drive here has: full rated torque at any speed the operator selects. Every advantage there was paid for. The Monarch's drive is the reason it can do what it does, and the reason it is the hardest machine here to keep running. Which brings the question back to where it started. Put a collet job with a threading operation on a 10EE and the Hardinge beats it. Put an instrument part on either, and the Schaublin beats both. Put a shaft that needs 20 feet of bed on any of the 3, and the pacemaker is the only machine still in the conversation. The Monarch 10EE wins on breadth rather than on any single category. It holds a spindle specification in millionths. It has the mass and the back gear to take a heavy cut, and its drive gives exact surface speed at any point in the range. No other machine on this list does all 3. That is a defensible claim for best all-round manual lathe, and it is a different claim from best manual lathe ever made. Which of these do you think is the best manual lathe ever made? Or do you have your own machine in mind? Comment down below. And if you enjoyed this episode, give the video a like and subscribe if you haven't already. See you in the next one.